Our next speaker is dear Professor Amr Abbadi. I see you are there. Hi, Amr. Nice for agreeing to talk in our seminar. Amr is an expert in blockchains, especially from his long experience in databases. He's a professor of computer science at the University of California, Santa Barbara, and he received his Bachelor of Engineering from Alexandria University in Egypt and the PhD from Cornell, and it's very well known in the area with many recognitions. And anyway, without further ado, let us welcome Amr Abbadi.
Thank you, Sergio. Thank you, Victor. I wish good morning. I wish I was with you in Mexico. I guess it's good evening for Vincent now, yeah? So I didn't catch, it's too early. I'm sorry, I didn't attend Vincent's talk. So I hope this talk presents a different perspective on blockchains. It's a foundational talk, so it is more of a tutorial style, and I understand that many in the audience might not have had much experiences with blockchain, so I'm going to do it little by little, and it might be at a different level from the end of the discussion that I felt was happening just at the end of the talk, of the previous talk. So this reflects various ideas and thoughts that I've had with various students of mine, Mohammed Amiri, Sujaya Maya, and Victor Zakhari, as well as my colleague Divya Agrawal. So this tutorial-like presentation reflects that. I assume I'll just lecture, and then at the end I'll take questions. Is that the mode of operation, Sergio?
I think it's...
if people want to ask me, it's fine.
Yeah, as you prefer, I think it's fine.
Okay, I'm fine. I'm fine. So let me just start a little bit historically about how banking systems come. And this is kind of the foundations of where databases come up. They were designed really to try and ensure atomic transactions across banks for financial operations. And the goal is that it should be fault tolerance, it should be consistent, all of the good things that databases over the years have been able to do. So what happens in a banking environment is you have various users, and typically users are members of different banks. And if there is a transaction that is taking place between two individuals, they each communicate, say I want to write a check or something. I write a check and the check goes to my bank, and then the recipient's bank, both of them coordinate with each other to ensure that eventually the money actually comes to the recipient. So that's kind of the traditional model, and you want to make sure that everybody the money, all my accounts are consistent, nothing bad happens, in spite of failures. So from a traditional database distributed systems approach, we have a transaction. You can think of it as a check, where basically you have identities of the person who is receiving the money. You need a public identity and a private signature for the sender of the money. So the sender sends a, try and do this. So here you have the recipient. This must be a public name that everybody understands. Then you have the private signature that nobody else can simulate, nobody else can cheat with. So we need a notion of identity and signatures. Then banks keep track of the amount of money, the balance that you have in some kind of a database. And the database typically can be thought of as containing historical information as well as the current state. So it will have a ledger of all the different transactions that took place. And these transactions move money from one entity to the other. We have to ensure correctness. So to ensure correctness, we need to ensure the notion of serializability, consistency, and you have various concurrency control protocols that have been developed to ensure that. Typically, you have a transaction log that ensures that if a failure happens, it captures information that hasn't completely been executed so that you can redo the information or undo certain operations that have occurred. This log needs to be persistent, and the traditional notion of persistency is that we put it on disk. So I put it on disk and I rely on the disk to survive failures, or if it isn't, then I have tertiary storage or some kind of stable information storage device. We also trust these banks. So we assume that the log is tamper-free, is immutable. Nobody's going to play around with it. Nobody's going to muck around and change a transaction that Sergio was giving to Vector and change it from $50 to $1 million. And now one party is very happy and the other party is not that happy. So we have these banks, and this is a picture of a real bank. It's called the Old Stone Bank. It's in near Brown University. And so it is big, it is solid, and it exudes trust. We put our money in banks, and banks take care of that money, and we trust the bank. What Bitcoin does and cryptocurrencies do is, let's get rid of these banks, and instead of that, we're going to have a large peer-to-peer network, a distributed system of many individuals. Actually, any individual who wants to be part of the system can be part of the system. And we are going to distribute this information among all these peers, and collectively, we are going to achieve the same properties that we were achieving with these trusted banks. So we'll have trust, we'll have notions of fault tolerance, all of these things. So we need to go back to this picture and now see how they're going to do it. And the way they do it in a Bitcoin or a cryptocurrency environment, we have various techniques. I'm going to focus on the approaches used by Bitcoin, but we can generalize this to others. We will need a notion of identity, and we'll need a notion of signature. So what do? We introduce this, we use digital signatures. So private and public digital signatures replace this notion of names and signatures. For a ledger, we're going to use what's called a blockchain. And if you want to think about abstractly, a blockchain is a highly fault-tolerant, resilient linked list. That's all that it is. It's basically a list of nodes that have been joined together by pointers. For transactions, we're going to need notions to replace issues like, or tools that we had before, like concurrency control. So instead of concurrency control, we're going to introduce a notion of way of achieving consensus, mining, proof of work, etc. So all these techniques fit into that part. And then for the log and the persistence of the log, instead of using a disk, we're going to use a traditional distributed approach for fault tolerance, which is to have replication. So instead of just one copy, we'll have many copies, and you'll have so many copies that we are guaranteed that somebody's going to survive and is going to be around. Then we need notions to ensure that the log itself cannot be played with. Now we know that anybody can have the log, so we have to be careful. Maybe somebody will change some parts of the log. So to avoid that, we introduce a notion of hash pointers, so the notion of hashing becomes important. So what I'll do in the next few minutes is to go through these different techniques. So there are signatures, public and private digital signatures. There's a linked list called a blockchain. And then we're going to explore how do we ensure tamper freedom, and how to add things to the log to make it functional, so to discover the notions of mining and proofs of work. So private and public keys, we need a notion, a very simple tool, and basically most of these blockchain systems use a public and private key encryption, where you have a generation function that gives you a private key and a public key. The public key is used to identify people. So instead of this encryption mechanism being used really for privacy or security, it's really being used for identification. I become known as my public key. Corresponding to my public key is a secret key that I hide in my pocket. Nobody else knows about it. And it is used to sign documents. With the public key, you can verify that the documents are actually signed by the person who signed it. So if you have a message or a transaction, it can be encrypted using the secret key. This generates an encrypted message that nobody can read unless they have the public key. Anybody with the public key can decrypt it and actually verify that it was sent by the sender who sent it. So they are unique to the signed document. Unlike analog signatures, here it is tied really to the document that you're talking about. They are mathematically hard to forge, but very easy to verify. And that's an important property because you're going to be verifying it a lot. So we have a document. You can sign it using a secret key. It generates a document with the signature. This is published. Anybody can get it. Anybody who has the public key can verify that this document was signed by this signature and decide that it is valid or invalid. So very simple notion. How do we use this for currencies is basically we have a series of digital signatures. So a chain of digital signature, the owner signs the coin and transfers it to the other. So let's consider the case where Alice has some Bitcoin and she wants to send it to Bob. So what she does is she attaches to the Bitcoin Bob's public key. Everybody knows that's Bob's name. So you attach it to it, and then Alice signs it using her private signature. That's the only one. So this verifies that she is the one who is giving the money to Bob. So this is signed. It generates a document that basically has the amount of money, Bob's public key, and Alice's signature. This can be publicized. Once it's out there, anybody with Alice's public key, and this is public knowledge, can verify that actually Alice gave to Bob the money. So now we know that Alice, the money now doesn't belong to Alice, but belongs to Bob. And this can be anybody who can see this information can verify this. So in general, we have a chain of this. The money just goes around. So we have a digital signature, Bitcoin that has been given to Bob by Alice. So she signs it, generates a document. And then now Bob can give it to Diana. Diana adds Diana's public key, signs it using his private signature, and passes it along. And now people know that not only that the money is with Diana, but they know that it came from Bob and Bob got the money from Alice. So you have actually the provenance of every piece of data in the system. You know the provenance of it, you know the lineage of it. So it's unlike regular money where if I show you a $1 bill, you don't know whether I got it from Sergio or from Victor or from my wife. But in a blockchain system, you would know the lineage of any piece of money in it. So there are lots of interesting questions we can ask at this level. We can ask, how do I combine this? Because as I add more and more signatures, this could become very big. So we have to make sure that the size remains constrained. And then how do I avoid a problem called double spending, which I will get into. So to combine, we use hashing, and actually hashing is pervasive throughout the blockchain system, is used a lot. So it's important to be comfortable with hashing. And basically, hashes are basically very similar to what we use in regular computer science. Here, these are more cryptographic hashes. What's important is that I can take a string of any length and hash it into a fixed length. So I know that the output is always 256 bits, for example, and it should be very efficient to compute. These cryptographic hash functions have lots of interesting properties. They are collision-free, meaning that with very high probability, no two different values, x and y, are going to hash to the same value. So they are going to have different values. More other interesting properties are that given the output of the hash, so given x, I've hashed it using h, hash function h, I produce h of x. Given the output, it is very difficult to know what the input was. So they are one-way functions. In fact, the only way you can figure out the output is to try all different inputs and to see which one is going to map to the value that you have. This leads us to the last property, which is also going to be used in blockchains, which is puzzle friendliness. Given a specific ID and a target set, it is hard to attach, to concatenate with this ID. So think of the ID as a pattern. Given a pattern, it's hard to find something to concatenate with it. So when I hash the entire concatenated string, I get to a particular string that has a certain pattern that can be specified by a target. This becomes very important when we get into mining. So I'll harp back onto this later on. So these are properties that we expect hash functions to have, and we're going to use them. So in Bitcoin, they use a particular cryptographic hash called the SHA-256, which basically takes a string of any length and maps it to a unique string of 256 bits. So we know that the output is always 256 bits. And as I said, they are, once you have one, it's very hard to figure out what is the input, or given one, it's very hard to even guess any kind of closeness. So for example, here in this example, I have a SHA-256 of lowercase abc. It gives me this random string of bits. And if I just change the C from lowercase to uppercase, I end up with a completely different random string. So having done SHA-256 of ABC or lowercase, it doesn't help me at all in figuring out the hash of another value that is even very close to it. So in general, we are going to use these hashes to make sure that the sizes of all of these are always 256. Now let's go to the problem of double spending. So if I have $1, I should have $1 with me, and I give it to Sergio, then I cannot at the same time give it to Vincent, or I cannot at the same time give it to Victor. Once it's with Sergio, it's gone. I don't have it anymore. However, in a digital world, I could actually make a copy and give it to somebody else. So for example, if Alice has some Bitcoins, she could actually, so Bob has some Bitcoins that he got from Alice. What he could do is he could say, I'm going to give it to Diana, but also to make a copy of it and say, I'm going to give it to Marty. And then sign it. Now this is going to be publicized, spread out to the world. Everybody can see that Bob actually wrote this. So if I got only this part, this transaction, I would see that Bob gave the money to Diana, and that is fine. So he gives it to Diana, and Diana verifies it and then sells him his car, her car. But at the same time, Marty is not aware of this, and Marty gets the signature that is saying that Bob gave him the money, and now he gives him the ring. So he sells him something else. So now Bob is very happy. Bob, for the same money, was able to do two things at the same time. So we have to develop notions, and this is critical for all cryptocurrencies, to develop some way of avoiding double spending. So if I gave you this problem and you're going to try and solve it, one can always try and say, come up with, this is a distributed problem. How do I solve it? I could solve it using a traditional centralized approach. So for example, we could have a central coordinator, if Bob, that keeps track of the money that Bob has or Trent has, and if Trent wants to give money to Diana, he just goes to the bank, and the bank checks if, and the central entity checks to see if it is this Trent has enough money or not, and then distributes the money again and keeps track of things. But this is exactly the traditional notion of banks. So the centralized approach kind of is reminiscent of the bank approach. It's a traditional approach. We could do it, but the whole philosophy of these cryptocurrencies is to try and come up with a completely distributed system that does not have specific entities that you trust to do the right thing. That we want to achieve this through a large-scale decentralized system. And this is where we come to the notion of blockchains, where basically every node in the system is going to maintain a ledger, and the ledger needs to capture the order in which the transactions were executed. And the order in which the transactions is executed is what is traditionally in a database context talks about as serializability, so that I know that if I have a bunch of transactions, at the end, the balance does reflect the transactions that were executed in that specific order, and that there wasn't any underpayment or overpayment. So you'll have all of the different nodes in the network need to agree on the transaction order and then serialize the transactions on every coin to prevent this problem of double spending. So let's get deeper into what is the blockchain and how does it maintain these things. So the ledger is going to be basically all of the transactions that were executed. Each node in the system is going to maintain a copy of the ledger. So this is complete replication. This is interesting because traditional database systems typically do replication for a fault tolerance reason, which means that I typically expect to have 1, 2, 3 failures. So the amount of replication is typically small. 7, 9, 3 even is often typically considered reasonable. Here you have large-scale replication. So it kind of changes the mindset of how we are going to approach problems. And these transactions are organized into blocks, where each block is connected to the other one using a pointer. So this is what I was talking about before. We have basically a linked list of blocks, and each block has a set of transactions that are being executed. So this is basically your blockchain. Of course, there are interesting questions to ask about it. And if you remember, one of the main problems I want to make sure of is that nobody can tamper with the content of the blockchain. So the blocks need to be connected in a way that avoids any tampering with. These pointers, since we are giving, notice, we are giving this blockchain to everybody in the system. So anybody can walk in. Somebody walks in from the door, we just, hey, hello, take this blockchain. Do I necessarily trust this person? Maybe not. Maybe yes, maybe no. We don't know. So we have to make sure that the structure that we are developing is tamper-free in its own right. So instead of having regular pointers, you have what are called hash pointers. So each block contains a hash of the previous block. And remember, these hashes are like SHA-256, so they're very difficult to reverse, etc. So tampering with the content, if anybody tampers with the content of one of these blocks, the hash information is going to be invalid and you can detect it. So for example, if somebody changed these two transactions so that they are a little bit different, then the hash of one of them does not correspond, then the hash of the subsequent block does not correspond to the previous block. And this makes it very hard to tamper with. So in general, we are going to make sure that if you have an inconsistent block, it's going to be detected. So the big picture now is that I have a bunch of nodes scattered all over the globe, and you have the ledger that is replicated everywhere. Most interesting question that we are interested in is how do we make progress? So I have a current state of the blockchain. What we would like to do is we would like to add a new block. So to add a new block, we need to validate that the new transactions are correct, are consistent. They don't underspend any amount of money. When you say you are spending this amount of money, you have to verify that your balance does have this money. So for example, so you have to make sure that within each block, the transactions do not conflict with each other, but also when you add a new block, it doesn't conflict and doesn't cause any inconsistencies with previous blocks. So nodes need to agree on the next block to be added to the system, and new assets are generated and registered in the system. So how do we do this? So we want to add a new block at the very head here. Well, if there's a bunch of nodes that have a data structure and you want them to take a consistent decision with each other, they need to execute consensus. So distributed systems have been working, the community has been working for a long time on developing consensus protocols in such systems. So that's what needs to be done at this point. So question can be, well, can we use traditional consensus protocols? For example, Paxos is very popular. So maybe we can. So what we do is we can add this particular block here. It came at one particular site. It executes a consensus protocol among all the nodes and then distributes the node to everybody else. So traditionally, all the participants in a consensus protocol like Paxos are known a priori. And this is where blockchains partition into two different kinds. We have permissioned blockchains and permissionless blockchains. So in a permissionless blockchain, and that's the kind that is used in most cryptocurrencies, nodes are free to enter and leave as they want. And the initial traditional well-known protocols are proof of work, for example, or proof of stake, and there are many others that have been proposed since then. On the other hand, in a permissioned blockchain environment, now you know the number of participants. So permissioned blockchain systems are being more and more used in database context. For example, supply chains, where you know the entities that are trying to communicate with each other, that are trying to execute something with each other. They just might trust, might not trust each other. So in an environment where you have producing like the fisherman is producing the fish, is catching the fish, gives it to the wholesale seller, who transfers it across the network with the trucking system. There are various entities, and they are known. So the participants are known a priori. They might trust each other. If they trust each other, we could use a Paxos-like algorithm, but more interestingly, they don't trust each other. And so we need to have some fault-tolerant protocol, and typically PBFT, or Byzantine fault-tolerant protocol, which tolerates malicious, untrusted information, works. So in a permissioned blockchain system, we have known, identified participants, and in this case, we can use any of the known fault-tolerant protocols. On the other hand, in a permissionless system, we have an unknown number of, we don't know who the participants are, and you typically reach consensus using mining. And here we replace communication, which is what happens in the traditional consensus approaches, with computation. So let me dig deeper into this approach of dealing with and introduce the notion of mining. So intuitively, networks try to do some computation and they race to solve some puzzle. The puzzle is expensive, computationally expensive, so it takes a fair amount of effort. And once a node is found, and once a solution is found, then you add it to the end of the blockchain, and you are the winner, so you can broadcast it to everybody. And this is attributed to this mythical character avatar called Nakamoto, who proposed blockchain, Bitcoin. So let's look at this a little bit more. So we have an entity and we have a blockchain. So think of this as a miner, and there are lots of miners potentially who are all trying to add a new block to the end of the blockchain. So we have a blockchain, it's replicated everywhere, and now every miner, there are all these miners that are trying to add more blocks to it. So typically you have all these users that are generating transactions. Every time I generate a transaction, Bob giving some money to Diana, Diana giving some money to Alice, etc. They send this, they broadcast it to all the possible miners. So this miner is sitting here and the miner gets a bunch of transactions. And so it creates a block. So it gets a whole bunch of transactions, it gets the block, and it creates a block. Now it wants to add the block to the blockchain. So let's look at this. So there's, in addition, there is this reward. If I am successful, I'm going to get some amount of money. This is what I get as a reward for the hard mining that I've been doing. Yeah. So this is the incentive, one of the incentives for the miner. In addition, a miner gets a reward for every transaction that is added to the block. So let's look a little bit deeper into what the block looks like. Well, it has the transactions, and it has the reward transaction, and it has a header. Let's focus a little bit on the header. It has a bunch of meta information, including a version number, timestamp. It has a pointer to the previous block, which is the hash of the previous block. So these are the hash pointers. It captures the basic information that is hidden inside of these transactions using a Merkle tree, and the root of the hash of the root of the Merkle tree captures this information. So again, this is meta information that is critical, so against tampering. And it has a notion of a nonce. So this is what it has a bunch of fixed things, and then it needs to add this nonce, which is basically a string of bits that it can concatenate. Remember the puzzle property that I mentioned earlier on of hashes. So it takes this string, it attaches it to the meta information, SHA-256 it using the hash function, and it has to make sure that it has a certain property. It's within a certain amount of difficulty that is specified. So the difficulty is adjusted dynamically as the system evolves every 2 weeks, so that it can change as the hardware changes. But basically, the difficulty is going to be so that it takes a certain amount of time to solve it, and this makes sure that there is a race. So it takes about 10 minutes to solve this difficulty. So if you remember the SHA-256, the output is 256 bits. The difficulty bits specify the number of initial zeros that need to be at the very left of the thing. And what you're going to be doing is you're going to try and hash it to come up with a string that has this many zeros. Now, if you recall, hash functions are one-way hash functions. As a result, this is not very easy. The only way I can do it is to exhaustively search the space. There is no efficient algorithm to reverse the output. So I want an outcome that looks certain, that has a certain pattern, but it's very hard for me to do it. The only way I can do it is through trial and error. So I have to explore the entire space to find it. And whoever finds it faster is the lucky one. So for example, here is an example of a header. I filled it up with some values. So we have a version number, we have the previous blockchain, etc. And what you're trying to do is to find something to put here, a string that you can put here. And the difficulty, let's say at this point, is to have 18 zeros at the very left. So I would like to SHA-256 this. So what I'm going to do is I'm going to try different attempts. So I'm going to SHA-256 all this information plus a zero. I'm going to try a zero. So any pattern. So I'm going to start with a zero. And I get this string. Does this thing have any initial zeros? No, it doesn't. So this doesn't work. I try a 1. 1 also doesn't work. I try a 2, 1, 0, for example. I end up with some zeros. Are they enough zeros? No, only 7 zeros. So I don't win. I keep on trying. So this is the life of a miner. Actually, we call it a complicated operation, but it's really a very boring operation. It's a loop that keeps on being executed, trying to figure out if there is something. And eventually he gets 18 zeros and he wins. And now this miner can announce the result of the block and add the block to the head of the blockchain. The difficulty, as I mentioned before, is expected. It changes approximately every 2 weeks. It's expected to approximately 10 minutes per mining, and the difficulty is adapted so that it more or less takes the same amount of time. So you basically multiply the old difficulty times the expected and the actual, and you figure out in a distributed fashion, each of them, how to change the blockchain. So in general, we have the mining, we have a blockchain. As you recall, we've distributed it across the network. And now when a new block comes in, this particular miner tries to mine. If the miner is successful, the miner broadcasts the new block to all nodes in the system. So in summary, to find a nonce, we are trying to find a nonce that results in being in a certain difficulty that is less than the difficulty that is bounded by that has this amount of space. The solution is a space. Once a block is found, a block is mined. It's very easy to verify. Remember, hash functions are one-way hash functions. One direction is very easy. All you have to do is to take all the entries in the block and SHA-256 it. It cannot be pre-computed because it depends on the current transactions in the block, cannot be stolen. The reward transaction is signed by the public key of the miner, and nodes basically accept the first block that they receive. There's one little problem here, is that I've been telling you all along we need to avoid double spending, and here we might have double spending because two miners, although it's unlikely, it is possible that they might find it at approximately the same time, and now they start broadcasting it in a concurrent way, and you might have two different blocks that are mined that connect the same blockchain. So what happens is we end up in a situation where we have two different miners. It's unlikely to happen, but it could happen that you have a transaction, a block, a green block, and the red block that is following the current blockchain. So transactions and now we have not verified any concurrency, any conflicts. All of these problems are back again on the table. So forks need to be eliminated. And Bitcoin takes a very pragmatic approach to solving this problem. It allows miners to continue, and miners just mine on the current longest chain that they see. So if you have two branches, and if I have one branch that is longer, I'm going to always adhere to that. So miners adhere to the longest chain, and the longest chain approach solves the problem of double mining. Of course, it means that double spending and double forking. Of course, it means that you will have to abort a whole bunch of transactions. So some transactions that were executed are being aborted. What does this mean? It means that once a block is added to the blockchain, we cannot assume that it is permanently there. So this is another relationship where databases, where we always worry about the abortion of transactions. We avoid the abortion of transactions in a pessimistic approach like with locking. However, there are optimistic approaches that allow this, and then you have to roll back those values. So what's happening here is we are actually going to abort these transactions and have to be resubmitted. So in general, you have a blockchain, and the blockchain can have forks. The longest chain is the fork that survives, and eventually all the transactions that are on not the longest chains are aborted. Blockchain can suffer from attacks, and this was in the original Nakamoto paper. As long as 51% of the computational power is not in malicious hands, we are okay. However, if the adversary has 51% of the power, computational power in the system, they could actually derail the system and could lead to double spending. So here is an example. If the adversary, if the bad guys have more than 50% of the computational power, you have a blockchain. They start mining and they keep on mining, and they end up double spending. So they spend a certain amount of information. So they create this transaction. They go down here and they use the money that was used by this transaction. But then they switch around and they start, and they let good guys go on and continue on this original line of a trail of the chain. But then because they have more computational power, they derail this and start a different chain, which continues and becomes the longest chain, and hence this money is going to be aborted and it messes up the system. I want, in the last few minutes, to give you another type of attack that was also proposed recently, 2018, called selfish mining, which also demonstrates how we think about these distributed systems and attacks in them. This was proposed by Gurun Emin Seriri at Cornell and his group. So, and it doesn't require 50%. In fact, a third is enough. Let's consider a system where we have a blockchain and we have an honest miner and some selfish miners. Selfish miners only have a third. They start mining and they find the next block, but they try to trick the system. So instead of advertising it, which is the right approach to do things if you were in this, if you were an honest miner, rather you hide it and let the honest miners continue mining on this block, which is, is obsolete. And what are the selfish miners going to do? They're going to continue mining on this block. So they are kind of thinking this will continue. So they're going to continue mining on this block, while the honest miner is still working on this block. Now there are two possible outcomes that can happen. The first outcome is that the selfish miner finds the following block. So they find the following block, they hide it until the honest miner finds a block, or the honest miners find a block, and now they reveal all their information. So now they have two blocks and the honest miner has lost the reward and has worked extra amount of time for nothing. That's one outcome. The alternative outcome is no, the honest miners, the selfish miner does not find the block first, but say the honest miners find the block first. Once the honest miner announces their block, then the selfish miner immediately announces their block, and now the computational power in the network has been divided into. The honest miners are going to be split in two. Half of them are going to work on the red block, half of them are going to work on the green block, and hence, given that the honest miners have a third of the computational power, they end up probably winning, and now the honest miner is probably going to lose again. So this is a different, interesting approach in which there is an attack that has been developed on blockchain. So I'm going to conclude now by just listing some limitations, and this has been a venue for a lot of interesting research. And if we had a whole school to develop things, I would have been happy to explore some of these issues. But you can go, and there are lots of papers that have been published on this. One issue is the high latency of confirmation. So as you've noticed, for a blockchain to add a block, it takes 10 minutes to do the mining. This was inherent in the original conception. But in a database system, we need latencies that are much faster than this. So we need approaches that avoid this. And this is the direction that a lot of the permissioned blockchains took. At the same time, you have very low transactions per second. So if you do the math, you are getting 3 to 7 transactions per second. In a credit card system, you're doing hundreds of thousands of transactions per second. So all of this has caused a lot of research, especially within the database community, looking at permissioned blockchain systems. The consistency guarantees that we give are probabilistic. As you saw, we can get into forks. We end up with these different approaches, the longest chain, etc. Another important thing is that because we have transparency, because miners need to validate transactions, we have a loss of privacy. So another direction of research has been to how to add confidentiality and privacy into the design of blockchains. And last but not least, and this is on one of the high lists of attacks on the traditional approaches, is that mining is very energy consuming, and that is not good because it's causing really a lot of havoc, and there are amazing statistics about how much energy is being used by all these mining approaches, especially proof of work. I'm going to stop here, and I'll be happy to take questions. Thank you very much.
Thank you, Amru, for the talk.
Thank you. This was basically a basic introduction to the basic foundations of blockchain. I hope this was appropriate.
Yes, thank you very much. Yeah.
Thank you.
Yeah, I was a bit surprised by what you said, that one of the, if I understood correctly, that one of the main differences with traditional databases is the amount of replication, that in blockchain you have essentially every participant all over the world replicating the database. But I wonder, I mean, if that is inherently necessary, because you made me think that in some sense what is important to have everybody participating is the way of coordinating, to sort of deciding how to extend the blockchain, to agree on how to change the blockchain. But the storage itself seems that there are many, well, I mean, many ways of solving the storage itself of the chain. So I wonder if naively maybe there could be some solution where you just store the chain in any, using any of the standard technologies, and just the very end of the chain, which is what is relevant for the agreement protocols, then you just kind of separate the concern of the replication by, and then the agreement itself is where everybody participates. Yeah.
You're right on, Sergio. So there are various approaches and various techniques that basically explore everything you've been saying. So one is, do I need everybody really to have it? And practically, often it's actually a small coterie of miners who are controlling the whole thing. So probably we can restrict it. And I think some of the approaches that have been developed since are doing that. That's one thing. The other thing is about the storage. Do we need the entire blockchain? And you're correct. All I need is like what's called the light blockchain part of it. So the headers would be enough, because that captures most of the information that I need for anything like this. There are validation issues that need to be discussed, but you're right. So I don't need the entire everything. I can capture a minimal amount of information about it. I still find, from an intellectual point of view, it's interesting to what are the challenges that the large-scale replication requires. And let's not worry too much about the storage, but just in terms of the management, the computational, and the communication, and how to scale that. So it raises intellectual challenges that I think are important to deal with and are worthwhile.
Yes, thank you, Amru. I think
I see some hands.
If people have questions, I think the way to ask them is by clicking at the question and answer banner in your Zoom meeting. And I think even after the talk, Amru will be able to answer them. Or
I see some hands up.
I think Rocio has a question.
Rocio, yeah.
Rocio has a question.
I don't know who controls this.
If you allow me, I will just talk. It's like we cannot post questions on the Q&A. Thank you. First of all, it was a great presentation. Thank you, Dr. Abbadi. I think that it was very clear, and there is, I'm sure, a lot of people in your audience that are not very sure about what blockchain and how it works, and it was super nice. Thank you very much. I just have a question. I just have a small question about what you mentioned about privacy versus transparency. Can you give us your opinion, what you think about that? Because many of the cryptocurrencies that use this technology that you just described argue that they are private, that if you do a transaction there, no one can really know who did it, and any information about that is be useful to identify yourself. What's your opinion about that? And thank you very much again.
Thank you. So there are multiple layers. All these questions have lots to dig into. So one of them is the question of tying the person, El Abbadi, with the identity, which is my public key. So there is this kind of level of anonymity that I can generate as many public keys as I want, actually, and hide behind them. So that's one level where we can have bad people come up and you don't know who they are, and they have a public key, and it's like you can't tell the difference whether the public key belongs to somebody like me who you know or somebody else. But for the validation of the content of the transaction, here there is no privacy, because you have to be able to validate that there is actually this amount of money that was subtracted from this account, and that the money actually went through this whole process. Now, especially in a database context, in a supply chain environment, we might be interacting between entities that do not want to reveal all the information to everybody in the system. Notice here, everybody in the system will know that the person with public ID number 12 gave to public ID number 20, and gave how much money, and you know kind of everything that has happened. I do not want this, because maybe I trust you, but I don't trust Sergio. I would like this information. If this is a transaction that is happening just between me and you, and not, I don't want Sergio to see that information. But the essence of the general blockchain system is that everybody can verify and see this information. So there's been a fair amount of work in the permissioned blockchain systems, and I would have loved to get more into the permissioned blockchain, because there's a lot of interesting confidentiality issues here, where we need to separate the data itself so that the verifiers don't see each other's information. That's kind of an answer. I hope it helps.
Thank you. Yeah, I think that encryption in this setting is different and very, very interesting. It will be a whole topic, and we are running out of time. So thank you for your answer.
We have another question from Alberto Cruz. Alberto, you are allowed to talk. Go ahead. Oh, it appears he is not listening. Well, we have one more question from Cynthia Palafox. She is a bachelor's student at UNAM. Can I learn blockchain on my own? Any piece of advice, Dr. Abbadi?
Yes, you can learn blockchain by your own. Any advice? Ask Sergio and Victor to have a school on blockchain for a week, and then we can all be together in Mexico and do something.
That would be great, for sure.
But I think Maurice Hurley, he maybe is here. I think they have
Yes.
a new book that
I think
recently published, so I could
advertise
it for Maurice also.
Yes. So please, I'll hand over to Maurice now. I think he's the next speaker. Yeah.
No, he is.
No. Oh, okay. But Maurice is the book out or not?
Yes.
Oh, the book is out.
Oh, the book is out. Okay, I haven't seen it yet. Okay, I need to get it. So
it's a place to start. I also have an undergraduate class at Brown with slides.
That would be awesome.
That reviewing the slides might be a good place to start. At least that has pointers to more detailed information.
Okay.
And I think also Vincent Gramoli has a large course online in Coursera or something on blockchains.
Yeah, he shared at the end of his presentation, and also the book that what you are talking about, Dr. Hurley, is on the webpage of the event. If any of the speakers would like, the people listening to this talk would like to know which book we are talking about, you can go there and find the link.
Yeah,
Antonio, who's also here, is a co-author or co-editor. So.
Oh, okay. So I'm working, but more in a permissioned environment. We're working on some textbook in that, but it's not yet ready.
Okay. Thank you very much.
Okay, thank you.
Bye. Thank you.
Bye. Thank you very
Bye.
much. Goodbye.
I hand over to Alejandro, I think. Is that right?
Yeah, that's right.
Bye. Thank you, everybody. Bye.